let's use print. We were able to predict 93% accuracy. For the purchase, we were able to have a precision of 86 and recall of 93. And the F1 score is 0.83. This is how you build a k-nearest neighbor classifier. Branches and leaves. The nodes represent the place where we want to ask a question or select an attribute. The leaves represent the output or class label using such a structure and the associated decision rules. The model predicts the value of a target value. The diagram on your screen demonstrates different parts of a decision tree. The root node represents a condition that is split into two results. It is then assumed that a decision node gets continued until the tree has no other condition left at this point. It is called the leaf node. This node has no further branches. Let us understand this better with an example. A maritime ship only moves forward when there is a low tide to save fuel. The below decision tree diagram represents the situation. The decision to split into nodes and leaves influences the model's accuracy. Decision trees use multiple algorithms to separate a node into two or more subnodes. The creation of subnodes divides the parent node into two parts, increasing the homogeneity of the subnodes. The purity of the node is directly connected to the target variable. Here are some algorithms that use decision trees. Remember, the type of target variables is an additional input for algorithm selection. ID3 extension of D3. See 4.5 successor of ID3. CART, classification and regression tree. CHA, ID chi-square automatic interaction. Detection performs multi-level splits when computing classification trees. MARES, multivariate adaptive regressions blinds. Benefits of decision trees. The tree structure helps capture the interactions between features within the data. Due to their visual representation, it is easy to interpret decision trees as compared to a multi-dimensional hyperplane. Disadvantages. Decision trees don't take linear relationships into account applications. Decision trees are effective in applications with nonlinear data sets. They're used in city planning, engineering, law, and many business applications. Applying decision tree. In this video, let's discuss how we can build a decision tree model. Let's start by importing the required libraries. We're using balanced scale data. Let's check the data info. Class name is the target variable which we are going to be predicting. You can also see that there are non-null values. Let's split the data into train and test with split ratio 70 and 30. Let's fit the decision tree model with criterion Gini. Let's keep the max depth as 3. Let's keep mini samples leaf as 5. Let's get the prediction. Let's check metrics. Let's create a target and see how the decision tree can be plotted. Now we have created a target. Let's plot the decision tree using an export tree. You can see how the decision tree has been spread. For example, left weight has been split into 2 points, less than 2.5, and greater than 2.5 within that. Again, the right distance has been divided into less than 1.5 and greater than 5, and so on. And then finally, we have got the class it's predicting. As you can see, from top to bottom, this is how it has been predicted. In this video, we saw how to build a decision tree classifier model and how to plot the tree. Random forest. Random forest is a machine learning technique that is used to solve regression as well as classification problems. It is an ensemble learning technique. That is, it combines multiple classifiers to solve a complex problem. The random forest algorithm consists of many decision trees. However, the key difference between typical decision trees and the random forest algo is that random forests only select a subset of the features, whereas decision trees consider all the feature splits that are possible. The diagram on the screen represents a random forest. Advantages: reduced risk of overfitting. In decision trees, data is fixed in nodes and leaves, so making predictions is easy. But in a random forest, it reduces the risk of overfitting, provides flexibility. Random forest is the most popular method, as it can handle the data set for the classification as well as for regression. Easy to determine. Random forest makes it easy to determine which variable or feature is more important and has the highest contribution towards the model. Disadvantages: time-consuming process. The algorithm works best with a large amount of data, but it also slows down the processing, requires more resources. It doesn't work with a small dataset, more complex. Interpreting the prediction of a forest can get complex. Applications. The algorithm is used across multiple industries. In finance, it reduces the time to manage a huge data set. It is used to evaluate prices in stock markets or in banks to process a loan. In large companies, random forest classifiers help identify the patterns of employee attrition. This was all about random forest. Applying random forest in this video, we will be building random forest regression. Let's start by importing the required library. Let's read the petrol consumption data. Based on these attributes, we'll be predicting the petrol consumption. All data types are in numeric, and there are no missing values. Let's create X and Y. Let's split the data into train and test. Let's rescale the data using a standard scaler. Now let's fit the random forest regressor with an estimator 20 and random state 0. From the fitted model, let's get the predicted value. Let's check the metric for train and test. We will print mean absolute error, root mean squared error, and R2 score for both train and test. You can see there is huge difference in metric value in terms of test and train. Using cross-validation, we will be able to minimize this. This is how we can implement random forest regressor. In case of classification problem, we will need to change the random forest regressor to random forest classifier, and we will be able to get the classifier model. Boruta explained. Boruta is a feature selection algorithm that works as a wrapper around random forest predictive modeling. We know it's crucial to get the most important feature, also known as feature selection. Boruta becomes useful to select features. When the dataset contains many features, we can recursively eliminate features in each iteration while fitting the random forest model. This results in minimum features, therefore it minimizes the error, and results in overproved input data that throw away some relevant features. In contrast, Boruta analyzes all the high and weakly connected features to the decision variable. Boruta captures all the features relevant to the dependent or target variable by following a certain feature selection method applications. Boruta is used majorly in the biomedical industry. Specific genes cause various health-related issues. It becomes quite complicated for the doctors to find precisely which gene is causing the health-related problems. Boruta is used to determine such genes. Automatic feature selection with Boruta. In this video, let's learn about automatic feature selection using Boruta. Let's start by importing the required libraries. We will be using English Premier Leave data. Let's read the data from the URL. As you can see, we have 1793 observations and 35 columns. There are no missing values, and all are non-null values. Let's split the data into X and Y columns. Here, let's drop position variable for X and for Y. We will have only position variable and then split the data into train and test. Let's fit the random forest classifiers. We will take all the features and fit the model and apply the same later. For feature selection, we will be using Boruta. The accuracy score for the model is 72.9%. Now, let's try to apply Boruta for the random forest model. We will need to fit the data by passing them in the array format. It is trying to get iterations for every 100 samples. It will also show how many variables are tentative and how many variables are confirmed. Based on that, the ranking will be formed. Let's print the ranking and also print the number of significant features. So out of 35 attributes, 31 is significant features, and it has ranking of 1, so it has dropped the rank of 2, 3, and so on. Let's see feature names by sorting ranks. So now we know the attributes, apart from rank 1. Using the important feature selection, let's fit the random forest classifier model. We are taking the same depth and estimator, however, will be fitting into the important features shortlisted from Boruta. As you can see, accuracy is 73, even though we have dropped 4 variables. The earlier accuracy was around 72. By dropping a few variables, we were able to increase the accuracy. So that's how we select important feature, using automatic features using Boruta. Support vector machine. Support vector machine (SVM) is a supervised machine learning algorithm used for both classification and regression challenges, but it is mainly utilized in classification-related problems. Before performing the classification of the task, let's plot the data points in an n-dimensional space, where n is the number of features in the data. Now, classification is performed on n-dimensional data using a hyperplane. The hyperplane helps to differentiate the classes. On the screen is a support vector algorithm. SVM is a type of algorithm that provides analysis of data for classification and regression. In SVM, the plotting is done in the dimension, the value of the data point, and the value of the coordinate in the dimension are the same. The hyperplane helps to classify two classes of the data in KNN. A kernel function is used to map lower dimensional data into higher dimensional data. SVM can be of two types. Linear SVM, it separates the data in a linear format. If the dataset is separated into two parts with the help of a straight line, then it is called linearly separable data. Nonlinear SVM, it is used when the data is non-linearly separated. If a dataset cannot be classified with the help of a straight line, then this data is termed nonlinear data, and the classifier used is called a nonlinear SVM classifier. Applications. Among other applications, SVM is used to classify the different avatars players use in games. For example, it can be used to classify the positive avatars and the negative avatars in a game. The SVM algorithm is best used to recommend ads. For example, in a kids channel, we will only see kids-relevant ads. SVM helps in segregating and recommending ads. SVM is also used to classify cataracts, a medical condition, during which the lens of the patient becomes progressively opaque, leading to blurred vision. This was all about the support vector machine. Applying support vector machine. In this video, we will be building a support vector mission algorithm. Let's start by importing the required library. Let's read the heart data. The acquired heart dataset is the attribute which we are trying to predict. Let's check the info. As you can see, we have 303 observations and 14 features. All the feature has a numeric data type, except for chest pain and thul, and there are no missing values as well. Let's describe and see basic statistics of these features. The average age is 54, standard deviation is 9. The average cholesterol is 246. Let's plot age and cholesterol. Also, let's see if there is any relation between age and cholesterol. Clearly, we can conclude as age increases, cholesterol is also high. We need to convert these two categorical variables to dummy variable. Let's create X and Y. Let's split the data into train and test. Let's import the grid search CV from the model selection. Let's use different parameter grid, which will be passed through SVC model using grid search CV. Let's fit the train data to the grid search. Now, let's print the best parameter. Based on the grid search, the best parameter are C at 10, gamma at 0.001, and kernel at RBF. Now let's check the accuracy of the train model. Accuracy here is 66%. Now let's check the confusion matrix for the test case. There are 11 cases where the model has misclassified as no instead of yes, and 7 cases are predicted as yes instead of no. Let's check the classification report. we have 70 accuracy, and the precision and recall are 0.70 and 0.59 respectively. So to recall, this is how we built the support vendor classifier model by using grid search CV. Cohen's kappa. Cohen's kappa is a statistical model used to measure the reliability of two raters who are rating the same quantity and identifies how frequently the raters are in agreement. To compare the predictions done by the machine learning model, we use Cohen's kappa. Many software packages in libraries like Caret, Weka, and scikit-learn provides Cohen's kappa. Cohen's kappa is calculated based on the confusion matrix, but it becomes complex to interpret as Cohen's kappa takes an imbalance in class distribution to calculate accuracy. Cohen's kappa is calculated with the formula you see on the screen. P0 is the accuracy of the model. PE is the measure of the agreement between the model predictions and the actual class values. Some key points about Cohen's kappa. Cohen's kappa is an excellent measure that handles multi-class and imbalanced class problems. The value of Cohen's kappa decreases with an increase in the difference between predicted and actual target classes. In balanced data, we get a higher Cohen's kappa value. Cohen's kappa is more informative than overall accuracy when working with unbalanced data. Let's have a quick recap of the lesson. In this lesson, we learned that classification algorithms are used to classify or categorize data into a class or category. They are also known as classifiers that map input data to a specific category. We also explored common classification algorithms like naive Bayes, linear classifiers, logistic regression, decision tree classifier, k-nearest neighbors, stochastic gradient descent, SGD classifier, random forests. Machine learning, unsupervised algorithms. The team was banding about ideas to extract patterns from the social media data available when Sheila heard that they would be using unsupervised learning to develop the machine learning models. She decided to update her knowledge. In this lesson, Sheila will explore the different types of unsupervised learning. She will analyze when to use algorithms and discuss different clustering types. She will learn how to calculate singular value decomposition and its applications. She will also discuss clustering algorithms like Perch, unsupervised algorithms. In this lesson, we discuss unsupervised algorithms. Let's see what these are. Unsupervised machine learning is a process of extracting patterns from the data. It deals with unlabeled datasets. This form of ML allows algorithms to work on their own to discover information from the data without any guidance. The primary task of the algos is to classify unsorted information according to patterns, differences, or similarities. Let's understand this better with the help of an example. A typical machine that is given raw data of elderly people may have no input on how to categorize it. Such a categorization is possible with the help of unsupervised learning algorithms, which detect patterns, differences, and similarities in such raw data. In our example, dataset of elderly people, the categorization could be done based on age, average time spent in hospital, the types of disease they're suffering from, and so on. The final categorization of this dataset helps us to derive some conclusions based on the different patterns generated from the data. This data represents formation of clusters according to the dataset features. So, what is the inference here? Via clustering, we found that 3 clusters are formed based on the average time spent in the hospital by a person. suffering from disease. After 1970, the death rate of patients suffering from cancer and heart disease reduced. The average time spent in the hospital also decreased. This indicates that the life expectancy of a 65-year-old person is higher today as compared to earlier years. The decreasing death rate might be due to technology excellence and copious information availability, also indicating progress in medical science. Here, we didn't know anything but learned from data. This is the goal of unsupervised machine learning. The machine derives insights from the data without being taught anything. Why unsupervised learning? This type of learning extracts many kinds of previously unknown patterns in the dataset. It also helps find features that may be useful for categorization. In this chapter, we learned that unsupervised machine learning algorithms have the ability to convert unsorted data into groups/categories based on similarities, patterns, and differences. In the next video, we will discuss types of unsupervised algorithms. Types of unsupervised algorithms. Unsupervised algorithms extract patterns from unlabeled or uncategorized data. They use clustering and association techniques to find the structure of the dataset and group them based on similarity. Clustering. Clustering techniques divide a set of data points into multiple clusters such that the data points within a cluster are similar to each other. In essence, clustering aims to segregate data points with similar traits. Association. An association rule involves finding the relationship between variables in a large data set. It determines the dependencies of one data item over another data item. Association rule learning often finds its application in market basket analysis. Some of the commonly used unsupervised learning algorithms are k-means clustering. This is an iterative clustering algorithm that groups the dataset into k predefined, non-overlapping clusters. K-medoids. This algorithm is similar to k-means, but with the requirement that cluster centers coincide with points in the data. Density-based spatial clustering of applications with noise dbScan. This algorithm finds core samples of high density and expands clusters from them. It is suitable for a data set containing clusters of similar density. Principal component analysis, PCA. This algorithm identifies patterns in a data set and simplifies the data set by reducing dimensionality. Agglomerative clustering. This algorithm forms a hierarchy of clusters by treating each data point as a separate cluster and then progressively merging similar clusters. This is repeated iteratively until all the clusters have been merged into one big cluster with all the data points. BIRCH is a memory-efficient online learning algorithm. It constructs a tree data structure with the cluster centroid being read off the leaf. When to use unsupervised algorithms? Unsupervised algorithms are useful when the goal is to extract data from unlabeled data and the output is not known. Unsupervised learning models are mainly used when the data points must be grouped based on similar traits. The relationship between different features of a large data set must be determined. The data inputs in a large data set with many features must be reduced to a manageable size. That is, the dimensionality of the input data must be reduced and anomalies in a data set must be detected. Applications of unsupervised learning algorithms. Unsupervised learning algorithms find many critical real-world applications, including market basket analysis, fraud detection, malware detection, customer segmentation, and targeted marketing campaigns. Thus, the ability of unsupervised algorithms to group unsorted data based on patterns, similarities, and differences make them an ideal choice for a myriad of applications. In the next video, We shall explore the different ways of visualizing the output of an unsupervised learning algorithm for maximum impact. Visualizing outputs. In this video, we're visualizing the output for an unsupervised algorithm. Let's import the data, and we're using Pokemon data. Let's drop the categorical variables as we will not be able to plot these variables. Let's create drop. We will not be able to plot the categorical variables. We will not be considering the names. It's only for reference. Let's create a k-means cluster and fit predict using only 2 data points, attack and defense. Let's create a centroid so that we will know the exact centroid points for each cluster. We will have 3 different colors, but now we will simply scatter them without any centroid. Let's create a scatter plot for attack and defense data points. As you can see, there are 3 different clusters created using k-means clusters. Let's create a scatter plot by highlighting data points for each cluster. Now, let's create a centroid point for each of the cluster. We will use for loop and iteros to create x and y values. Now, let's create a centroid point for each of the cluster. we can see how data is spread away from the centroid. You can use the convex method instead of creating a centroid. This is how we can create the plot data for cluster case. Performance parameters. Machine learning is the science of creating predictive models based on data. The output here is probabilistic. Hence, evaluating the performance of the model becomes quite important. Various metrics are used to evaluate the performance of a model. The parameters, or performance metrics, must be carefully chosen based on the type of problem, as supervised or an unsupervised learning problem. We know that the end goal of an unsupervised learning algorithm is to create clusters of similar objects. A model is deemed to perform well if members of a given cluster exhibit similar traits. Let us explore the metrics used to evaluate the performance of clustering algorithms. Two commonly used metrics are silhouette coefficient and Dunn's index. Silhouette coefficient. The silhouette coefficient is a measure of similarity of a sample to its own cluster when compared to the other clusters. The value of the coefficient ranges from -1 to +1. A lower value indicates that the sample is less cohesive to its own cluster. A higher value indicates a high cohesion. The coefficient is the average distance between a sample and all remaining points in the same cluster divided by the average distance between the sample and all the points in the next closest cluster. Here, A is the average distance between the sample and all remaining points in the same cluster, and B is the average distance between the sample and the points in the next closest cluster. The silhouette coefficient for a group of samples is the average of the silhouette coefficient for each sample. The score again lies between +1 and -1. A score of +1 indicates a highly dense cluster and -1 indicates an incorrect cluster. If the score is around 0, then we can infer that the clusters overlap. The higher the score, the denser and well separated the cluster will be. Dunn's index. The Dunn's index DI is used to determine sets of clusters that are cohesive and well separated. A higher DI value indicates better clustering. Dunn's index can be obtained by dividing the minimum inter-cluster distance by the maximum inter-cluster distance. Both the silhouette coefficient and Dunn's index are internal performance evaluation schemes where the result is based on the cluster data itself. This was about the performance parameters for clustering algorithms. In the next video, we shall discuss clustering types. Clustering types. Clustering is an unsupervised machine learning technique that involves grouping or clustering of data points. The goal of the clustering exercise is to classify data into distinct groups so that each group offers similar observations. The output generated by running the clustering algorithm over a dataset should be understandable and solve the business problem at hand correctly. We have various types of clustering methods, and we can choose any of them depending on the type of problem we are trying to solve. There are 4 important types of clustering: centroid-based clustering, density clustering, distribution clustering, and hierarchical clustering. We shall learn about these types in subsequent videos. In the next video, we will learn about hierarchical clustering. Hierarchical clustering. Hierarchical clustering, also known as hierarchical cluster analysis, HCA, is an unsupervised clustering algorithm. It adopts either a bottom-to-top approach to grouping data, known as agglomerative HCA, or a top-to-bottom approach, known as divisive HCA. Every data point in our dataset is deemed to be a cluster first, as similarities are observed between the closest pairs of data points. Objects are added to a specific cluster that, as objects deemed similar, are grouped into clusters. The endpoint of the algorithm is reached when we have a set of clusters where each cluster is distinct from every other cluster in the dataset, and the objects within each cluster are similar to each other. Let us understand how this algorithm works with a real-world analogy. Say you have a dataset of n different types of animals. We will start by assuming that each animal is a distinct cluster by itself, that is, n clusters. We will take some two closest data points and make them into a cluster, say cats and dogs. We now have n and 1 clusters. The process repeats as we group all mammals into a cluster, all reptiles into another, all fish into a third cluster, and so on. The mammals, reptiles, and fish can then be grouped into the vertebrate cluster. Similarly, an invertebrate cluster can be formed of insects, corals, and arachnids. Finally, we have one large cluster of animals. As you can see, hierarchical clustering results in the creation of a tree-shaped structure known as a dendrogram. A dendrogram is a visual interpretation of the hierarchical connection of items. Its goal is to find the best approach to assign items to a cluster based on similarities and dissimilarities. How do you choose the number of clusters to be created? To choose the number of clusters, identify the longest line that traverses the maximum vertical distance without intersecting any of the merging points in the dendrogram. You can see this line labeled 1 in the dendrogram on your screen. After this, draw a horizontal line. The number of vertical lines it intersects is the optimal number of clusters. In the figure you see on your screen, the optimal number of clusters is 3. Applications of HCA. HCA is a very useful algorithm, helping us in many different areas. For instance, this technique can be used to track the spread of viruses, such as COVID-19. If data such as location of viral detection and number of infected people is extracted, HCA can help us identify the origin of the spread of the virus. HCA can help with customer segmentation activities as well. Without any prior input about the number of clusters or groups, HCA can help a company or industry segment their customers to understand their behavior better. This is a crucial activity in product design and marketing. This was about hierarchical clustering. In the next video, we will understand it better with a demo. Applying hierarchical clustering. In this video, we'll see how to build a hierarchical clustering. Let's start by importing the required library. Hierarchical clustering. Hierarchical clustering, also known as hierarchical cluster analysis, HCA, is an unsupervised clustering algorithm. It adopts either a bottom-to-top approach to grouping data, known as agglomerative HCA, or a top-to-bottom approach, known as divisive HCA. Every data point in our dataset is deemed to be a cluster first, as similarities are observed between the closest pairs of data points. Objects are added to a specific cluster that, as objects deemed similar, are grouped into clusters. The endpoint of the algorithm is reached when we have a set of clusters where each cluster is distinct from every other cluster in the dataset, and the objects within each cluster are similar to each other. Let us understand how this algorithm works with a real-world analogy. Say you have a dataset of n different types of animals. We will start by assuming that each animal is a distinct cluster by itself, that is, n clusters. We will take some two closest data points and make them into a cluster, say cats and dogs. We now have n and 1 clusters. The process repeats as we group all mammals into a cluster, all reptiles into another, all fish into a third cluster, and so on. The mammals, reptiles, and fish can then be grouped into the vertebrate cluster. Similarly, an invertebrate cluster can be formed of insects, corals, and arachnids. Finally, we have one large cluster of animals. As you can see, hierarchical clustering results in the creation of a tree-shaped structure known as a dendrogram. A dendrogram is a visual interpretation of the hierarchical connection of items. Its goal is to find the best approach to assign items to a cluster based on similarities and dissimilarities. How do you choose the number of clusters to be created? To choose the number of clusters, identify the longest line that traverses the maximum vertical distance without intersecting any of the merging points in the dendrogram. You can see this line labeled 1 in the dendrogram on your screen. After this, draw a horizontal line. The number of vertical lines it intersects is the optimal number of clusters. In the figure you see on your screen, the optimal number of clusters is 3. Applications of HCA. HCA is a very useful algorithm, helping us in many different areas. For instance, this technique can be used to track the spread of viruses, such as COVID-19. If data such as location of viral detection and number of infected people is extracted, HCA can help us identify the origin of the spread of the virus. HCA can help with customer segmentation activities as well. Without any prior input about the number of clusters or groups, HCA can help a company or industry segment their customers to understand their behavior better. This is a crucial activity in product design and marketing. This was about hierarchical clustering. In the next video, we will understand it better with a demo. Applying hierarchical clustering. In this video, we'll see how to build a hierarchical clustering. Let's start by importing the required library. We're using customer data from a mall. We have their gender, age, income, and spending score. Let's check DF info. There are non-null values or no missing values. Let's create DF1. Let's ignore gender. We will just consider age, annual income, and spending to build a clustering algorithm. Let's import the cluster hierarchy. Now, let's plot. On the screen, you can see customer dendrograms. As you can see, there are different clusters that have been created. Light blue represents one cluster, red represents one cluster, and entire green represents one whole cluster. However, we can see that there are more than 3 clusters. Let's use aglometric clustering and see if we can identify more than 3 clusters. For affinity, we're using a Euclidean distance. Let's check the labels and plot it. As you can see, within this spread, it has created 5 different clusters. The colors green, yellow, blue, and violet represents a cluster each. This is how we can use the dendrogram and then create a cluster. K-means clustering. The K-means clustering algorithm is an unsupervised machine learning algorithm. It groups unlabeled data into clusters by identifying K number of centroids. Further, it assigns every data point to the closest cluster by calculating and using the pairwise Euclidean distance between points. What you see on the screen is a flowchart for K-means clustering. Let's go through the process, step by step. Step 1. Select the number of K clusters. Here we take K equals 2. Step 2. From the dataset, select K number of random points as centroids. Since our K value was 2, 2 random centroids, yellow and blue, are considered. Step 3. Allot all data points to the nearest available cluster centroid. Here all data points are assigned to the nearest centroid, either blue or yellow. Step 4. Calculate and place the newly generated centroid at each cluster. Now a centroid is generated considering the newly formed clusters. Step 5. Reassign each data point to the new closest centroid. If no reassignment happens, then stop, else go to step 4. Here, the black color data point was close to the blue cluster but far from its centroid, hence it got assigned to the yellow cluster. As you can see, K-means rapidly forms clusters of data points from which we can derive inferences. Where is this algorithm applied? Insurance fraud detection. New claims can be identified using historical data on fraudulent claims based on their closeness to clusters, indicating fraudulent patterns. Identification of crime localities in a city. Crime localities in a city can be clustered using city data, such as names of neighborhoods or types of crimes. To summarize, the K-means clustering algorithm is a centroid-based algorithm that groups unlabeled data into K number of clusters, each with one centroid. It requires the number of clusters to be predefined. In the next video, we shall discuss the K-medoids algorithm, which is very similar to the K-means clustering algorithm. K-medoids algorithm. The K-medoids algorithm is a classical partitioning technique where we group a dataset into K number of clusters. Here, K is predefined before executing the algorithm. The value of K can be validated by silhouette methods. Medoids are representative objects of a dataset or a cluster within a dataset whose sum of dissimilarities to all the objects in the cluster is minimal. This algorithm is similar to the K-means clustering algorithm. It uses the concept of dissimilarity to form clustering groups. It is used especially when the centroid or the mean cannot be derived out of similar data points. The algo is more robust against noise and outliers as it minimizes general pairwise dissimilarities instead of a sum of squared Euclidean distances. Let us now understand the similarities and differences between K-medoids and the K-means clustering algorithms. Both the algorithms are divisional, that is, these algorithms break the data set up into groups. K-means attempts to decrease the total squared error, whereas K-medoids decreases the sum of dissimilarities between points designated to be in a cluster and a point designated as the center of that cluster. Unlike the K-means algorithm, K-medoids chooses data points as centers. K-medoids is very flexible and can be used with any similarity measure, whereas K-means fails to converge. K-means must only be used with distances that are consistent with the mean. In this video, we discussed K-medoids clustering. In the next video, we shall demonstrate the working of K-means algorithm. Applying K-means clustering. In this video, we will be building a K-mean clustering. Let's import the required libraries. We are using the datasets of mall customers. Let's implement k-mean with just 3 clusters. These 3 clusters might not be the optimum value of k. Let's create a scatter plot with centroid for 3 clusters. As we can see in this plot, there can be more than 3 clusters. For now, we have the clusters in red, blue, and green. Let's try to get the optimal k-value by plotting an elbow method. We can either choose the k-value as 5 or 6. In this case, we're using the k-value as 5. Depending on the dataset and problem, we can decide the lowest within cluster, sum of square or WCSS. Let's create a scatter plot with centroid for 5 clusters. Clearly, the data has split into 5 different clusters. So this is how we can build the k-means cluster algorithm. The k-nearest neighbors, or KNN, algorithm is an easy-to-use supervised machine learning algorithm. It assumes a similarity between available cases and a new case, and bins the new case into a category that is most similar to available categories. KNN is used for both regression and classification problems. KNN is a non-parametric algorithm. That is, it does not make any assumption about the data. It is also called a lazy algorithm as it does not learn immediately from the training set. The training set is just stored. Instead, learning is delayed until a test instance is given before it performs any action, such as classification on the dataset. How KNN works. The KNN algorithm uses the concept of feature similarity to predict new data point values. Any new data point is assigned a value based on how closely it matches the data points within the training dataset. Here is a sequence of steps that demonstrate how KNN works. Load the data, initialize k, that is, any integer that determines the nearest data points to a given data point. Calculate the distance between the new data point and the current example from the data set. Note that we use the Euclidean, Manhattan, or Hamming methods to make this calculation, most commonly the straight-line Euclidean method. Add the distance calculated and the index of the example to an ordered collection. Sort the ordered collection in ascending order. From the smallest to the largest, choose the highest. k rows from the sorted array,